Okay, welcome to video 2, which is technically video 3 because we did 1A and 1B because that's how we roll. We're going to talk about internal energy here. So if you take out your notes here, I'm going to give you some terminologies here and then we're going to talk about it a little more. So first let's start with energy, and energy is defined as the capacity to do work or to produce heat, which begs the question, what is heat? Well, heat involves the transfer of energy between two objects due to a temperature difference. It is important to understand that heat is not a substance. You cannot have heat. Heat is how energy is transferred. So we need to say it, heat is not. The other part of our definition for energy is that it's the ability to do work or capacity to do work. So we need to define work, and work is defined as a force acting over a distance. That's a terrible handwritten thing here. So if I just apply a force on something, so let's say I'm applying a force on something, and let's say it's a box, and that box doesn't move, no work is being done. So just be aware of that. Finally, there's something else called a state function, which the AP board has said that they're not going to spend that much time with, so we're just going to barely touch on it here. State function depends only on an object's, there's not very much room here, so I'm going to write up here, an object's present state. In other words, it's pathway independent. So the idea would be this: if I were to draw like a mountain range, like this is supposed to be a mountain. That's terrible. And there's snow or whatever here. And let's say I wanted to take the height of the mountain, that is a state function because that's never going to change. It's pathway independent. From the bottom of the mountain to the top of the mountain, that change in that height, that is pathway independent. But you could go a bunch of ways to go up the hill like this, but ultimately, like the distance you travel, that's not pathway independent, but the height would always be pathway independent. So state function is something that doesn't matter how you get there, it's just that you're there. So let's move on and let's talk about internal energy. So internal energy is, again, one of these things we have to know something about. It's essentially the sum of all the kinetic and potential energies in a system. Now, the internal energy of a system can be changed by either doing work on a system or having a system do work, or if energy is added or taken away. So there's an internal energy question. So essentially what you need to take is that the internal energy of something, that's essentially just the amount of energy that's in a system. Now, if that energy changes, there's only two ways that an energy can change, and that is due to either work or heat being either applied or taken away. So the equation we're going to use here is the internal energy equation. You need to jot this down, where W is work being done on the system or by the system, and Q is the amount of heat gained or lost. So it's kind of a useless equation, but what it does let us know is that whenever the energy of a system changes, it's based on either whether or not heat is being applied or given off, and whether work is being done on the system or being done by the system. Now, let me remind you of a couple things here. Everything in thermodynamics has a sign. The sign does not, the positive or negative, does not tell you whether or not you have a negative amount. It tells you direction. So remember the spoiled child that we just talked about in the previous video. So thermodynamic quantities, those that are having to do with, always have a number and a sign. So that indicates the direction of flow. So let's just walk through this here. So if I have energy that's going into a system, then we say that the Q is positive. If I have energy that's flowing out of the system, and the type of energy we're talking about right now is heat, then we say that the Q is negative. Similarly, if work is being done on the system, we say that work is positive. And if the system does work on the surroundings, we say that work is negative. So again, the system is the spoiled child. Whatever is done to it is good. Whatever it has to do itself is bad. So let's move on to the next page here, and let's see how this might be applied and how they might expect us to be able to do things even when we don't understand what they're giving us here. So they give us an equation here, 2OH gas going to H2O, and I wish I'd made that as a subscript, but I haven't. And it says, which of the following statements correctly describes the signs of Q and W for the following exothermic process? And that's kind of a big deal because exothermic, if you remember from before, means that we are losing heat. So we're going to have negative Q. That just tells us that from the get-go, we're losing energy. So if we take a look at our answer choices here, there are only two where they have Q as negative, A and C. Every other one has Q as positive or Q as 0. So it can only be A or C. So if you were like lost on the question, you're like, I don't understand what to do in this. At the very least, you could look at this and say it's exothermic, so we know which two of these that we can choose from. It's a 50-50 shot. But let's go a little bit better than that. So when we take a look at this, we see how here we have a gas turning into a liquid. And what does that mean exactly? Well, it means that the work is happening by the system. We are actually causing work to be done. So, I'm sorry. Can I reboot on that one? So when we take a look now at work is a little bit different because we need to understand whether or not the system, the reaction, is doing work or work is being done on it. And if you take a look here, we have a bunch of gas particles, right? So if we have a bunch of gas particles and the end result is they go from a gas, 2 moles of a gas, to a liquid, do you see how it's getting scrunched from that to like a liquid form, which is going to be kind of a lot more compressed? So what's happening is, picture if you would like some sort of outer pressure, like a piston, pushing it down like a trash compactor, pushing it down on all sides, right? I don't know, I'm not gonna do it on this side. But it takes some outside force, squishes down everything to a smaller quantity. So the outside is doing work on the system by compressing it down. Which, by the way, before we go any farther, let me just kind of remind you how this works, because when we're comparing a gas to a liquid and a solid, gas particles are incredibly far spread apart. Gas particles have no limit as to how far apart they can be. Whereas a liquid, the intermolecular forces in a liquid and in a solid are significantly greater. In fact, if I were to compare a liquid molecules together, I might draw them something like this, and they're all kind of moving back. These are not bonds. They're just kind of vibrating back and forth, right? And if I had a solid, they'd be much more compact, right? If I was doing the same thing, but they would also be moving around. The difference between these two right here is almost negligible. So if I were to compare these two right here and say which one of these is more disordered, or if we were comparing the amount of work to go from here to here or here to here, it's not very much work to get a liquid to go into a solid, or a solid to go into liquid. But to get a gas to turn into a liquid or a solid, or a liquid or solid to turn into a gas, a significant amount of work needs to be done because there's a huge difference between here and here. So going back to our original problem here, we can take a look and we say, well, if work is being done on the system, we're squishing from a gas down to a liquid, that must mean that the W is positive, so that means that our choice has to be C. So now we're gonna do it kind of a hurry up mode, and we're gonna do a few more examples of this. So if you take a look at this scenario right here, they say it's performed at constant external pressure, and they wanna know simply about work. Is work being done on the system or being done by the surroundings? Which I think I said is the same thing. So is the system doing work or is the outside doing work on it? So in essence, what we can do is just look at the states of matter. So you see again here, do you see on this side here, we have a solid and we have 2 moles of a gas, right? And that's going to 1 mole, because the coefficients indicate the number of moles of a solid. So essentially, aren't we going from a gas to a solid? And not only that, we're doing 2 moles of a gas to 1 mole of a solid. We also have another mole of a solid here, but again, if you're dealing with a gas, the compression of a gas into a solid requires a great deal of work being done on the system. So in this case right here, our work would be positive. Here we have 1 mole of an aqueous solution and 1 mole of an aqueous solution. So I'm going to do this over here. We have 2 moles of AQ over here. And on the other side, we have 1 mole of a solid and we have 1 mole of aqueous. Again, aqueous is just a liquid that has particles in it. So if we're comparing this here, we're going from essentially a liquid, 2 moles of a liquid, to a mole of a liquid and a mole of aqueous. And again, the difference between a solid and a liquid, or an aqueous and a liquid, is so small in terms of the amount of work required to make one go into the other, that we'd actually consider that one side to the other would be negligible. So they actually would say the work here is meh, it's negligible. Similarly over here, do you see how we have 1 mole of a gas and we have 1 mole of a gas on the other side? And oh, by the way, as a kicker, we have a solid, but the solid is like, boo, it doesn't really do anything. So again, we're going from 1 mole of a gas to 1 mole of a gas, essentially. There's no work being done. Lastly, if we take a look here, do you see we have 1 mole of a gas on this side? And on this side, we have 1 mole of a solid. and we have 2 moles of a gas. So you see how we're going from 1 mole of a gas to 2 moles of a gas. So what is happening in this case here? Isn't the reaction itself expanding, or isn't it pushing outwards? So that means that work is being done by the system as it expands out. So in this case here, we'd have to say that work is negative. That kind of makes sense? Okay. Now, one of the things they often do is they like to deal with pistons. Pistons are their favorite. And so we pretend that the system is what's on the inside here of this piston. If you notice here, initially we have a little bit of space down below, and then at the end, the gas is pushed up. There's force acting on the outside, but if you take a look here, it's acted up, and so you're going to have work being done by the system, which means that all in all, we know if I go from here to here, that the work is going to be negative, because we've gone from a little bit of gas expanding out to a lot more gas expanding out. More distance has been covered from here to here. Now, I want to show you a formula that we use in chemistry, but it's now I'm going to show you a formula that we use, and I'm going to show you how we derive it. It's not incredibly important, but what you should know is that pressure is always equal to force over area. That is our go-to formula. So if we write it in here, we're just going to write, I don't know why I put it over there instead of writing it here in your notes. Pressure is equal to force over area. And when we rearrange that, we can just get force is equal to pressure times area. That's just a simple manipulation. The formula for work is force acting over a particular distance. So if we write work is equal to force acting over a change in height, work is equal to force being applied over some distance. That D can sometimes be replaced with like a change in height, or something where something's being significantly moved. But if we sub this into the equation up above, we end up with force is equal to work. That force, we plug it in here, we equal force is equal to pressure times area times the change in height. So all we've done is we've just taken force and we've rearranged this equation and plugged it into here. Now, if we rearrange this equation here, area times height, we probably know this is volume. So if we can go from here to here and say that work is equal to pressure times volume. Now, when we take a look at that, that leads us to like the really, really important equation, and that is this right here. Work is equal to negative P change in V. Now, I mentioned this before, but we always write our signs as if the system is king. In other words, since the gas is doing the work in our piston example, so if we take a look back at our piston example here, since the gas is expanding here, work is negative. So in order to rearrange our equation, we need to have our work be equal to negative P change in V. Now, sometimes you'll see it'll be written like this, but I hope you understand it does not matter what side the negative is on. That being said, this is the equation that is showing work being done by a gas that's expanding. And they often give you, like, if they give you a problem, they show you a cylinder and they show that the container's expanding, you're going to come back to this formula to get to your work. Now, before we go any farther here, there's an issue of units. There are some conversions that allow us to go back between different units. And so the first one is this: joules, which is I'll make a capital J because that's the unit for work, is equal to a kilogram times meters per second squared. Jot that down because that's going to allow us to get from work to units where we're dealing with work, mass, and time. Length and time. And the other conversion is this: 101.3 kilojoules is equal to 1 liter atmosphere. So this is going to be, we're going to use this stuff later on. Hopefully this has been helpful. I'll see you in the next video.